Hello and welcome to the lesson on projectile motion. So your goal today, I want you to be able to explain and solve real-world problems involving projectile motion. So as we move through, what is projectile motion? What are some examples? Projectile motion is an object that is moving in two dimensions. So we did introduce this, you did see this in the grade 11 course. So basically a projectile is moving in both the y and x direction simultaneously. Okay, so it would have two components. It would have the x component of motion, and it'll have the y component of motion. So that is what projectile motion is. So the object is moving up or down, I guess, and left or right. So those are our directions for motion. And for any projectile, its velocity or displacement vector, so depending on what we're talking about, will consist of two components, a horizontal component and a vertical component. So this means that a projectile question must be broken into two parts, horizontal and vertical. And we talked about this in the grade 11 course, so I'm just going to do a quick review on that. If you have, for example, a launch vector, a velocity vector v, then it will be broken into our two components. We remember from just adding and subtracting vectors that we can algebraically represent a vector by using the formula magnitude of v cos theta I plus magnitude of v sine theta j. So knowing that information, we break it into our horizontal and our vertical. So those are the two components that we're interested in. And again, that magnitude of v cos theta I, okay, that's our x component. And the sine is our y component. So our horizontal, to calculate our v1 in the horizontal, it will be equal to the magnitude, or what the initial velocity was, cos theta of the angle. And for the horizontal in the grade 12 course, unless we have a rocket pack on, it will be 0 meters per second squared. That would be meters per second, your velocity. In the vertical, your v1 will be the magnitude of the velocity sine theta. That would be meters per second. And our acceleration will be we're using 10 this year. Now it's simple, 10 meters per second squared. And that's always down. So those are always true for the grade 12 course. So there are your components. And anytime we run into projectile motion in this particular unit, you can know that your V1 and A's are going to be consistent. So we're just using that vector notation that we talked about in previous. All right, so now I want to bring up a computer app here for you, and I want to show you a couple of things, and I'll have that website on there hopefully for you. So this is just a simple calculation or simple demonstration of projectile motion. So I've got the settings as it showed up here, and if I hit fire, we can see the initial information here. All right, so I'm just going to pause. I'm going to take a screen capture and put it into my notes so it's a little easier for me to talk about. You can just give yourself a sketch. And what I want to do is I want to just change a couple of things here for you. I want to change the velocity. I want to change the angle. So I'm going to choose or move my, keep the same angle, and we're going to increase the velocity by, can I double it from 50 to 100? Not quite. So let's go 75. So we'll make it a little bit larger there. And we will fire the second one. And you can see that once you launch or increase the velocity, it still maintains that symmetric shape, that parabolic shape. And that's under ideal conditions, and that's what we're really focused on this year. And one last one I want to look at is I'm going to return the firing velocity back down to 50 again. Oops. And I'm going to change that angle. So that's at 70 degrees. So let's go half. We'll go to 35 degrees. So this is the blue. The blue is the original. The new color here was the same velocity, but a much lower angle. Okay. So we lowered the angle of attack. However, maintain the velocity. So definitely 35 degrees, the object will travel farther, but in the original, at the higher angle, you get more height. So it depends on the situation, whether you're trying to get over something or whether you want to get some distance. And we're going to talk about how to optimize your distance as we move through. So as I said, if you want to play with this a little bit and try some different scenarios, because there are many, you can change mass and see what the difference is, change your angle. You can do whatever you kind of want to do with it. So I'll put that, make sure that applet website's up on my website under the videos there, so you can try it out yourself and play a little bit with that. So let's go back, and I took screen captures on each of the three here. So on the side here, I have notes, point form stuff that I want to talk about. So what are some of the things that we notice from those three examples that I did? Well, the vertical component is affected by gravity, okay? So in all cases here, and I'm only going to put it in certain locations here, right? In each case, your acceleration is constant. Acceleration is always down, and our acceleration is the 10 meters per second squared down. All right, so it doesn't matter what projectile or which one I chose, the acceleration will always be down. And the vertical component then changes with height. So for example, it is traveling at the same speed here, upward, so Vy, you can hardly read that, try to do a little better job. So there's my velocity upward, here's my velocity upward, and they are the same. Okay, go down to this picture here. My upward velocity will be much, much larger than it would be, say, as we get closer to the top. All right. Now, when oops, I made a bit of a boo-boo there. Sorry about that. The ball is falling. So the velocity will be the same magnitude as it was across, but now it's heading in the down direction. Sorry about that. So here, if we go straight across from that one, there will be a velocity downward. It'll be the same magnitude, just the direction switched. Maximum height occurs at the vertex. That's why in the grade 10 course, we're so concerned with finding vertex. So the vertex is where max height occurs. All right, max mins. At the maximum height, vertical velocity will be 0. That's that transition from moving upward to downward. So for a very brief moment in time, those max or mins, so right there, right there, right there, each max min, there will be a change in velocity from upward to downward. For that moment in time, that brief moment in time, that will be a value of 0. Next, vertical components are often affected by Earth's gravity. Not often, should be always. They are affected by Earth's gravity, meaning there will be acceleration, and I already talked about that up above with the green vectors that I drew on there. We're still not going to have horizontal acceleration. We're not going to talk about rocket packs and so on and so forth. Projectiles follow a parabolic path under ideal conditions, and again, we're in a physics class, so we are talking about ideal conditions. When you specialize in engineering or physics or sciences, then I let you to worry about the real world effects here, but what we want to do is get an understanding of how they should behave. Then you can have that conversation of why it didn't behave that way during your experiment. And finally, the path is symmetrical when they start and finish on the same elevations. So what that's saying is that this distance here is equal. So this distance here is whatever, it's x. That distance will also be the same. So we are symmetrical in our parabola. So this parabola is identical to this one, except it's a mirror image in the axis of symmetry. All right, that's what that's called there. It's our axis of symmetry. All right. So there we are. There are the properties I want you to take away from projectile motion and be able to identify on a graph. Now the other thing I want to put in there, horizontal. If the horizontal component, if there's no acceleration in the horizontal, then our horizontal vector, so our velocity is going to be the same everywhere when we draw the horizontal. Okay, so horizontal vectors will be of the same magnitude throughout. Okay, so let's talk about a free-falling object for a second. If I drop an object, so I'll do the 3 stages, here's impact, or I send it out as a projectile, and it follows a parabolic path. So here's path 1, and then here's path 2, follows that parabolic path. Then when we do an analysis here, if you're just dropping it, okay, if you drop the object, V1 would be 0 in the horizontal, and we're going to look at both cases here. So if it's dropped, V1 equals 0 meters per second. When it gets to this stage here horizontally, so our new V, I'm going to call it V2, and same thing here, V2. So I'm working on the same elevation. So if I draw a line across with the same elevation, what would V2 equal? Well, if we use our motion formulas, V2 equals V1 plus AT. V1 was 0, so it would be 10t here, so however long it fell for. Now, if you go to the other side, the projectile, it's the exact same formula. All right, same formula. V1 was still 0 when it rolled off the top there, so it's still 10t. All right, so you can see that the vertical component remains the same all the way through. If we rolled this off the end of the table with a velocity of, let's pick an arbitrary number here. Let's go 5 meters per second. Okay. The projectile motion then has a component of 5 meters per second, but because it's in that x direction, it does not influence the y direction. So all it's doing is it's creating that displacement from the base of what we rolled it off of. Okay, so there's my displacement. That horizontal vector plays no role in how fast the ball is dropped, or how fast the ball is dropping. Okay, it's that whole I and J component. The I doesn't affect the J component and vice versa. So that 5 meters per second will remain constant all the way or throughout the drop. Okay, however, the green vectors, the V2 vectors, they will adjust as they drop, because it'll be the same thing down here. This will be larger because the new V2 here is also 10t. But if I go location A and location B, time B is greater than time A, which means the ball's been falling longer and influenced by gravity longer. So that velocity, that final velocity, would be much, much bigger than it was partway through the fall. And again, it's the exact same calculation. It's going to be gravity times the length of time for the fall to get your velocity. All right. So there are some of the properties when we're dealing with projectile motion that it's important to remember. Horizontal, no acceleration. So maybe I'll just rewrite it here. Horizontal, no acceleration. And the vertical, acceleration again, it's 10 meters per second squared down. Okay, it doesn't matter whether the object was dropped or whether you drove a car off a cliff, you will land at the same time regardless, and I got a couple demos in class to emphasize that. All right, so in the next video we'll get into some examples just to refresh your memory from last year.